All right, being recorded. All right, we left off yesterday talking about geometric pitch and effective pitch. And the difference between the two is slip. And now we're going to move on to aerodynamic forces of a propeller. Let's go to the top of the page. There we go. So I'm on point number 4 for aerodynamic forces. Aerodynamic forces. All right, so basically we have 5 forces here. I almost consider these two over here on the right, far right, they're sort of in their own category to me, because we're going to talk about them and use them a lot when we get into constant speed propellers. And A, B, and C, they're just there. And it's something that is on the propeller, but it doesn't really do anything for us. It's just, but we're going to use these other ones. Well, really the centrifugal twisting force, the last one, we're going to use that a lot to do work in a propeller and make it do what we want it to do. So I could actually almost say A through D are just there and they don't really help us do anything. They're just a hindrance. E actually can help out. But so notice there's two centrifugal forces. There's centrifugal force A and centrifugal force E over here. And you really need to keep those two completely separate because they are completely and totally different. So there's centrifugal and centrifugal twisting. All right, so centrifugal force, just like the picture shows here, it's just trying to take the blade and just rip it out of the hub. And that is why you don't stand in line with the blades, because if anything did come ripping out of the hub, it'll go flying straight out at you. So I don't stand.
Like the paint. The paint would
Yeah, I am.
What's that?
paint would hit you.
And the paint would hit you. Yes, the paint slides off and it hits you. So centrifugal force. Torque bending force, as you can see by the picture, it's almost like the lead lag, if you will, when you think about helicopters, except it just causes it to lag. It doesn't cause it to ever lead. It just starts bending back around. The thrust bending force is if you were to grab the tip and pull. And while I'm looking at that and thinking about it, I will tell you one of the things that just makes me nuts, and I'm really freaked out about my airplane, is I do not like people touching my propeller at all, period, ever. People tend to grab propellers and move airplanes around with propellers. And the theory would be, I suppose, that, hey, if the propeller's strong enough to pull the aircraft through air, it's obviously strong enough to, a few pounds of force while it's on the ground. It's actually false. And I've talked to prop shops who have said they've actually seen propellers almost get ruined, especially on a hot day when the metal's really hot and people will grab it out here and just, pilots do. They put their hand right out here somewhere and just start pulling on the prop. It bends it. And it bends it forward and it throws out the tracking on it. And then it starts to get inefficient and all kinds of problems. So if you see me, if I do it, I will touch it right here next to the spinner, except I think my partner, he pushed on the spinner and broke it. And that was very, very expensive. So it's always a good idea to don't touch the dang prop. So, all right, thrust bending force pulls it forward. The aerodynamic twisting force is really, you just take a look at this and as the wing that it is. And when you guys studied aerodynamics, those of you that have, you know that with a wing, it actually wants to twist simply because of where the center of pressure is versus the center of mass and the center of rotation on it. So another way to look at it is it's a wing and it's got lift, and it wants to lift. I guess we can use this picture right here, and that just makes the whole thing want to twist around this way. So it just causes a twist. However, we'll go over one more. There's this centrifugal twisting force, and keep in mind, we've actually looking at it in a completely different plane of rotation. Here's the hub right here, and so it's spinning around to the right. This is almost hard to do without actually standing in front of you and doing it. What happens is because of the mass, there's so much more weight on the propeller out here than there is back here. When you swing something around, this mass wants to rotate, actually wants to rotate this way and be in line with everything. It doesn't want to come back out. So this one wants to bring it towards feather. This would be feather up here. And this wants to bring it all the way to a flat pitch, completely flat. And that's where it wants to be. So this one, the aerodynamic twisting force, is fighting the centrifugal, but the aerodynamic never wins, never, ever. I can't think of any situation because there just isn't enough of the aerodynamic twisting force to overcome the sheer weight of this propeller spinning. And so it just wants to go completely flat into the flat pitch position. Now, if it's a fixed pitch, what?
When you say flat pitch, do you mean flat blade angle?
Yes, thank you. Flat blade angle. But see how I'm going to say pitch? So it wants to pull it this way. Aerodynamic wants to bring it into feather, and centrifugal wants to bring it into, it's called low pitch when you're talking about constant speed props. This is what we call it. So, but it is. It's the zero blade angle. Well, I hate to say that because, but yeah, I'm going to say that, the zero blade angle. So because the blade angle is relative to the rotation. So it would be zero blade angle. So centrifugal brings it into that zero blade angle. These forces, A, B, and C, absolutely, they're out there taking place. You've got the centrifugal wanting to rip the blades out of the hub. You have the torque bending force that wants to make them lag. And you got the thrust bending force, which is going to bring it forward a little bit. And oh, by the way, why doesn't it bend the blades when you're running it? Because there's an even thrust load over the whole thing. And as opposed to when you just grab it by your hand and yank on it. So it does bend forward, but it snaps back. So A, B, and C, yes, they're always out there. They're always happening. I'm going to tell you about them. And then almost from this point on, we're never going to talk about it again because it really doesn't do anything for us. Then I'm going to say D, I'm almost never going to talk about it again because it's there, but it doesn't do anything. And then when we get into our next segment, we start talking about constant speed propellers. We're going to be talking about centrifugal twisting force almost every other minute. It's like, well, but the centrifugal twisting force makes it do this. So this is the one you have to have the best understanding of, but these are on the test. So, all right, the whole thing is just called aerodynamic forces. Lump it all in. So, all right. So the first one we had is centrifugal force. An act, or a force, I should say a force. A force that tends to throw the blades away from the hubs. A force that tends to throw the blades away from the hubs. Tends to throw the blades away from the hub. It causes stretching of the blades. It causes stretching of the blades. Makes paint slide off. It is the greatest force. The greatest force acting on a propeller. Acting on a prop. I found this in a book and I was absolutely astonished. I didn't write down where I got it from. May exceed, and that's the key word here, 7,500 times the weight of the prop. The weight of the prop. Constant speed props are pretty stinking heavy, but a lot of that is in the hub, so I would discount the hub weight. Oh man, I shouldn't have. Let me think here. Over here. I can find this here. Look up the type certificate data sheet for 140. This really isn't a type certificate data sheet. It's a spec sheet. Because it's the plane that came to mind. There we go. Let's see if this is it. Yeah, okay, pull this over so you can see what I'm looking at. So I was just thinking about this. So this is a type certificate data sheet for a Cessna 140. And I told you they're a little bit different because they were done under car. But let me see, empty weight, CG range, fuel, we should get into engine limits. That's my red line. Empty weight, maximum weight, seatbelts, control surface here. You go down to my notes. And this is why I like this one, because they actually give you a little more information. But here we go. So how much does a Sentinel's propeller weigh? 11 pounds. I bet that's wood. Fixed metal. Yeah. So 22 pounds. So you're looking at a prop that's 22 pounds. So 22 times 7,500. So that's 165,000 pounds of force trying to rip the prop apart. But I'll be fair and say that it's going in opposite directions. So I could divide it by half. So that'd just be 11 times, well, I just add a 0. So that's 75,000 pounds going each way on that thing. So to tell you that there's a lot of stress on these blades is to kind of understate how much stress is on them. And this is why, and I respect that. This is why I do not mess around with propellers. There's a lot coming apart on here, or wanting to come apart. They hate you and they want to come apart. They want to do a dynamic disassembly. And I had one of my first flight instructors, he told me about a flight he was on where he lost a piece of the spinner. Something came off on the spinner. And of course the spinner is right there near the center line of the propeller. It's not out at the tip. So it would be even worse if he lost a piece of a tip. And he said that it shook that airplane so hard that all he could, I mean, it was unbelievable. He had to shut that engine down and dead stick it. There was no way, he said, that engine was going to stay in. And so what could happen is the engine would shake. So if you lose a piece of the prop or something, the engine would shake so hard that it could shake it right out of its mounts and then fall out. And when it falls off, that throws out your weight and balance. And as I say, you're going to back up all the way to the earth. And that is not a good thing to do. So, you know, I guess I tell you that to say, I take it very serious, especially these constant speeds, because they do come apart. They're made to come apart. You don't want them to come apart in flight. So, all right, we have torque bending force. Torque bending force, and that is because of the air restriction. So due to air restriction, not restriction, resistance, air resistance. Air resistance, due to air resistance, tends to bend the blades in a direction opposite rotation. Tends to bend the blades in a direction opposite of rotation. Opposite of rotation. And when you talk to prop shops and the inspection of these things, they'll tell you, yeah, they actually do. They'll take a set and they will get bent and they'll stay bent because of the constant bending forces on it. And they start to get inefficient and all kinds of problems. The other interesting thing about propellers that I don't think I mentioned it in here. So, you know, we have fixed pitch props is really what we're talking about. And of course, we're going to talk about constant speeds later, but it stands to reason a constant speed prop has moving parts and therefore it needs to be inspected and, you know, it's got bearings and all that stuff. But you think, okay, well, if you have a fixed pitch prop, There's zero moving parts. It is just a moving part. It's just a hunk of metal, or it's a hunk of wood, and or composite these days. So what is there, especially with a metal one? What is there to do to it? Why would you overhaul it? But what they do to these props is they bring them in and they actually take off a surface layer of aluminum. They make the whole thing thinner. And what that does is because the prop develops stresses in it, and these stresses rise to the surface. And by taking off a layer of the aluminum, you remove the stress out of the blade so it doesn't crack, which I think is just crazy, but that's what they tell me. So torque bending force. So
What's the TBO on a prop like that's on your airplane?
It's usually you do it with the engine. So 2,000 hours. But that's fixed. Constant speeds can vary greatly, and you really want to stick to the calendar time on those things, because sitting around is one of the worst things for them. If you're using it more often, you're better off. But when they sit, that's a bad thing. So you want to go, I think is it every 10 years on those?
Is that because all the moving parts?
Moving parts, and then even just sitting and the way the moisture collects and the stresses that are involved. But I tell you, constant speed props, they are stupid expensive. Harry, have you ever had to deal with your prop on your plane?
No, I've only had it about a year, so I haven't had to do much with the prop.
Okay. So, and we're going to talk about some of the props here, and they do product improvements, and it's funny when you talk to prop shops and the things that happen to these props, it's just, you just shake your head. And that's one of the big things about being a mechanic. You have to be so careful with propellers, because if you do something to it that's slightly stupid and you have to send it in for something like a reseal, like something stupid, like you go to grease it and use the wrong grease, or you put too much grease in it. You're like, oh man, I used the wrong grease, or I put too much. What am I going to do? You can't fix that. You have to send it into a prop shop, and they're going to say, okay, we've got to do a disassembly, clean, and reassemble. But just like now you're talking about a repair station. Repair stations, that's why FA loves them, because they have a higher standard. And so they take it apart and they look at it and go, well, shoot, yeah, it just came in for a reseal, but man, I got to tell you, you got corrosion on this part, so we got to replace it. You've got a crack on this one, so we got to replace it. And this is a mandatory replacement item when you disassemble it. So yeah, we're just going to do a reseal. An overhaul would have cost you 20 grand, but your reseal is only going to cost you 19,000. For an extra grand, we'll call it an overhaul. And you're like, for just because you re-grease something, you just spent 20 grand. So that's how quickly the costs can mount up on these. So when I was considering for a small period of time there, while I was drinking heavily, purchasing a 182, which I'd still love to have, that was one of my big things. It's funny. It's like, it's just, I'm familiar with engines, so engines don't necessarily scare me, but they scare me enough to know they're really expensive. So everything I was looking at was like, the first thing I looked at was, what's the TBO on the prop? How long has it been since the prop was overhauled? Because, that's a huge expense. Imagine if you can get a good deal on a 182, I mean, a great deal, and you only spend $70,000 on it. And then 6 months later, you just need to have your prop overhauled for 20. That's a pretty expensive plane. So, all right, thrust bending force. That was kind of the soapbox, sorry, but the thrust load that tends to bend the blades forward, the thrust load that tends to bend the blade forward, forward as the aircraft is pulled through the air, pulled through the air. And of course, if it's pushing it through the air, the opposite.
Would there really even be a thrust bending force with the air because of the air coming at it, or is it more? I don't.
Is it because there's low
absolutely
pressure in front of the prop?
Yeah, it's just pulling it forward. And it's pushing backwards, so that just pushes it forward.
Okay, that makes sense.
All right, aerodynamic twisting force. You got to throw in the twisting in there. Aerodynamic twisting force. All right, this tends to twist the propeller toward a high blade angle. Tends to twist. And this is, I know we're talking really about fixed pitch propellers. So this doesn't play that much into fixed pitch, but imagine we have a constant speed, which does twist the blades. The blade angle varies depending on what the pilot wants. So the pilot can actually do that. So it's on a rotating bearing in there. So it does have a pronounced effect. So it tends to twist the prop, toward a high blade angle, toward a high blade angle. And I'm going to put feather, just so you get used to me saying that, towards feather. So sometimes I'll just say towards feather, and you can, high blade angle is feather. And you know which way is feather is, right? All right. Center of lift, this is because center of lift, or center of pressure. Sometimes it's called center of pressure. I like center of lift, I don't know. Is forward of the center of rotation. Is forward of the center of rotation. Which is the midpoint there. So center of lift, pressure is forward of the center of rotation. And because of that, it tends to pull the blade up around that center of rotation, as the picture showed. I will not duplicate the picture. And then the big one. Both the centrifugals are our big ones. Centrifugal twisting force. So remember, we have just centrifugal and then centrifugal twisting. All right, so due to the mass of the blade, the force tends to move the blade. Force tends to move the blade toward a lower blade angle, toward a lower blade angle. And then I could say flatten out. Flatten out is the colloquial term. I'll abbreviate it CTF because it just is a little difficult to write centrifugal twisting force constantly. So CTF is greater than aerodynamic. So the CTF is greater than the aerodynamic. So the centrifugal twisting force is always going to be the most pronounced and force that we were actually going to consider ourselves quite often. So this force is used to operate constant speed props. You guys remember Tom?
Yes.
Yeah, unfortunately.
Be nice. He did a video, And I'll have to find it if I can, and I'll post it to Canvas. And if you want to, you can look at I think it's like an hour and a half long, but he found some program and spent like half a year developing this program that would show the airflow through a propeller with and without twist. So I have to find it. I'll admit I didn't watch the whole thing, but I watched some of it. It was good.
Is he in the video?
Yeah. All right, tip speed. Nothing new here. We've talked a lot about tip speed over the course of our classes here. So tip speed is the principal limiting factor for propeller efficiency. Is the principal. You know, I always spell this type of principal, C-I-P, principal. My notes actually have it as principal, P-A-L, and I actually think principal is right, but oh well. I know it's also the principal of a school is PAL, but when it's the primary thing, I think it's actually spelled different. Limiting factor, I was not an English major. For propeller efficiency, prop efficiency. All right, tip speed is the principal limiting factor for propeller efficiency. Excessive speed. So I've told you before, and I think we've kind of left it just hang there at this, that if the tip speed reaches a transonic region, not supersonic, just even gets near transonic, pressure waves are set up. And then for you that have had guys that have had aerodynamics of Phil, you'll understand supersonic and the pressure wave that is built up, and the pressure wave is going to cause a stall in that area. And so we could just kind of say that, go, well, it's going to stall out, right? And we know that a stall is bad. And so you're going to start stalling out the tip of your prop. And of course that stall would work its way down. And then before you know it, the prop wouldn't work because it's stalled out. Well, if that were the case, that is the case, but that's not the real problem here. So excessive speed causes flutter and vibration. Now this flutter thing, it's one of those things that I have a hard time wrapping my mind around. If you look at control surfaces on an airplane, even the ailerons and elevator on my little Cessna 150, they're balanced. And so they have to be taken off the aircraft and put on these balancing blades. And there's lead weights in there because they have to get this perfect balance. And to me, that seems so weird because I just see a surface that is bolted to another surface with a steel rod that is controlling it and steel cables that are controlling it. And I think, well, how is it possible that if it doesn't balance in a certain way that it would flutter? And flutter happens, the control surface actually, well, flutter is a great word. It flutters. I mean, it just goes nutso. I was going to say ape-ass, and will actually rip itself right off the airplane. And this is what was happening to the Bonanzas. The V-tail Bonanzas was the first, I think, plane that really started experiencing this. And the reason why is because that particular plane was so fast. It was one of the first general aviation airplanes that was reaching these high speeds. And it was a unique V-tail design. And there are some other reasons why I don't remember off the top of my head. But anyway, so several of them would break up in flight. And so they found out that it was a flutter problem. And my memory is coming back. And it's something to do with the cables weren't tight enough and stuff. And so anyway, but they had to correct all that. So flutter is this weird thing. And if you see, I should get a video, but I've seen some videos of some of the classes I've taken where it's actually shown a flutter happen in flight. It absolutely is astounding. You cannot believe what you're actually watching. It looks like the aircraft, the empennage, like on a V-tail, like the whole empennage or the rotorvators, they turn to liquid, like they're made of jello, and the whole thing is just fluttering around and shaking like a bowl of jello, and you're like, whoa! And it just goes to a point where it just separates from the aircraft, and the aircraft breaks up in flight. Vibration, you understand vibration. But anyway, this excessive tip speed actually causes that to happen to the propeller. And the propeller then would almost look like it's made out of jello, and it just starts fluttering all over the place. And then the stresses that are induced in it cause it to have what we say is a dynamic disassembly. So, when people talk about flutter, unless you've actually seen it or really studied a little bit and watched what happens, you kind of glance over it. But flutter is kind of an instantaneous death to the aircraft and to the occupants. So it's really a big deal. So,
is there any videos of it?
I don't know. We could always pull up the old Google. Let me see. Look at it.
I'll check this out real quick. Hold on.
Detail flutter. Let me see. Fidges. I don't know. I may have to find one at
Scotty found it.
Scotty's found one. You got the link there? You can.
Yeah, that one of the PA-30 is the one I watched. It's a good one.
This one? 24 seconds. I don't know if I got that much time. There's no sound. Oh yeah, that is a pretty good one. That was a great one. There you go. That's made out of jello.
Is there any way that you can like correct it, like just slow down immediately, or what?
Sure. Yeah. You slow in a situation like that, you would slow down immediately. But this is what happens when aircraft exceed their design speed. Things like that start to happen, which is why it's a big deal. Some people just think, well, it's just aerodynamic forces get a little heavy on it, but nope, that's what they do. They get all whacked out crazy. And so you can take that, and this is completely outside of this class now, but you take that, and then this is what freaks me out, is that you get mechanics out there who don't think about that stuff, and they do repairs to control surfaces or paint them, and they don't do any balancing. So you do anything to a control surface, you're supposed to take it completely off and go through the whole balancing thing. And you guys are going to learn how to balance them in second year. It's not some magic thing. It's quite simple. You just have some lead weight and you just make sure it's balanced within what it's supposed to be. And then you do it and call it a day. So, so when you see how easy it is, you just wonder, well, then why didn't you do it? So anyway, so tip speed must be below speed of sound, must be below.
They didn't do it so they could save time in SeaWorld.
Yes. Save time, go to funeral. Must be below speed of sound. I actually would say it's got to be below transonic even. So to keep, let me see, to prevent tips from exceeding, exceeding sonic speed. What do we do? Well, one of the things is, well, first of all, I should put this. Red line engine. I know at some point I've got this in my notes, so I'm just going to wait till I get there. You actually have a lot of these aircraft, especially a lot of aircraft, have really bizarre markings on their tachometer. And they'll have yellow arcs, and then they may have a red arc in the middle of the tachometer. And you're like, what the heck? Why would you have a red mark in the middle? And what that is some engine propeller combinations. And it really is. It's that prop on that engine on that plane, if you can believe it. You take that engine and prop and put it on a different plane, or take that prop and put it on a different engine, you don't have this problem. But there are some engine prop combinations that they can't get rid of the flutter or the vibrations. It set up a vibration within the engine and prop that actually ruins the prop. And so what they do is they will put a red or yellow arc in there where you can only be in that RPM range as you're going to something else. You cannot stop and operate in that range. You can accelerate through it, you can decelerate through it, but you can't be in it. But when I say, I'll put here red line engine, that's max RPM, of course, max RPM.
Is that per manufacturer?
Absolutely. It's on the type
Okay.
certificate data sheet, note number 3. And it's got to be placarded. Let's see. So what else can we do? Well, you can gear down the engine. Gear. You can use a geared engine, or you speed up the engine or slow down the prop, or shorten the prop. Shorten the prop. Shorten the prop and widen the blades, if you will, but I'll just put shorten the prop. Prop. Propeller load. This is kind of a fast point here, but for some reason I felt like I wanted to make it when I wrote it. So the faster the propeller turns, the faster the prop turns, the more power it absorbs. And of course the prop, or uses, I could say, absorbs, or I could use the word uses. I always like stuff like this. I don't know why. It varies. Varies with the cube of RPM. Varies with the cube of RPM. So in other words, double the RPM. And you will have 8 times, because that's 2 cubed is 8. You will have 8 times the power required, 8 times the power, W, power, I'll say used, absorbed. So within the propeller, what it's actually doing out there is about 80% of horsepower is used for thrust, and the remaining 20% of horsepower is used for friction and slippage. And because slippage, sorry, P slippage, I'll try to do better. Because they added the word slippage into this statement that I found, I'm going to say that means that we're talking about a prop that is up to 80% efficient, which it doesn't quite line up to what I was thinking, or sorry, not thinking, but our notes. But one of the thoughts I did have about this statement, I just couldn't find it, or they didn't go into enough depth for me to pick up on this, but it's potential. And I think that of this is of what is used, what is actually used. So I would say that probably, because we're talking about 80%, and what do we say? Propellers are upwards to, what was my exact statement yesterday?
Wasn't it 80%?
Yeah, but it was like low 80.
7?
Let me see.
I thought it was 0 to 85.
Was it? Yeah, it was about 85.
I remember 0 to 85%.
All right, we'll go 0 to 85. So, then this would line up with total. So I'll just pull that out. So that would line up within the total output of the engine. So total output of the engine, 80% of horsepower is used for thrust, up to, I would say, and maybe a little bit more. And then 20% is used for friction and slippage, which slippage is remember the difference between geometric and effective pitch. This one, this point, efficiency. I don't know if efficiency is the right word, but we're going with it. We already talked a little about efficiency. This is, a little bit different look at it, but this goes back to what we talked about in engine class when we're talking about the difference between horsepower. And then I said there's brake horsepower, and then you get into thrust horsepower. So this is what gets into thrust horsepower. I know it's 418. You'll be okay. Someone have to explain to me the Jeep death of wobble.
You hit a bump and your tires go back and forth extremely rapidly.
I had that happen in a Ford pickup.
Yep.
My Jeep doesn't go fast enough. I've had it up to 50 miles an hour.
It's one of the ones you just hold.
So actual amount of horsepower, that an engine propeller unit, engine of horsepower, that an engine / prop combination, or unit, I'll say unit because it's easier to spell unit transform into thrust.
The death wobble in like a vehicle doesn't have to do with speed.
Oh yeah. It's yeah, we hit a bump right and hit the brakes at the same time. I've had that. It sucks. All right, 420, almost 419 my time. So I will give you guys a quick break here.